So you have a ray of light coming in. The angle that it makes with the normal to the interface between the two media is, let's say it's θ1. And then when it goes into the water, it's going to change direction. And it might be going in this direction. And this change in direction happens because of a change in speed. So as light, as a wave goes from one medium to another, its speed changes. And the speed of light in air is a little bit faster than in water. So let's say that this angle is θ2. And this is the angle made by the refracted ray, the ray that went into the water with the normal. So that's θ2, right? Now, whenever the light hits the interface, some of the light will also be reflected. So that I didn't draw that over here, but for completeness, I should also draw the reflected ray here, which will make the same angle as the incident ray. And that is the law of reflection that we also discussed yesterday. But we are not going to bother with the reflected ray for now. We'll just focus on the one that went inside. But there'll always be a little bit of reflection whenever you have refraction. All right. So Snell's law says that sine θ1 divided by sine θ2 is equal to V1 divided by V2, right? So Snell's law, but it's written in a slightly different way. So I'll just introduce that for now. So this is Snell's law. Now, I told you that the speed of an electromagnetic wave is different depending on the medium that it's traveling in, right? The index is the ratio of the speed of light in vacuum to the speed of light in the medium. That's the definition of index of refraction. So the index of refraction n, that's the symbol for the index of refraction, is defined as the speed of light in vacuum, which has its own letter c, divided by the speed of light in a particular medium. So you can clearly see that n will always be greater than 1, right? Because it's not possible for it to have a speed greater than c. So n will always be greater than 1. So n is called the index of refraction. And n does not just depend on the material. It also depends on the wavelength or the frequency of the light that's being used, that's propagating through that medium, right? So now the frequencies or wavelengths of visible light, and we are only going to be talking about visible light for the most part, they're all very close to each other, because we saw that the wavelength range for visible light is something like around 400 to 750 nanometers, something like that. So the wavelengths of all the visible light waves is pretty much the same, very close to each other. And so their frequencies are also very close to each other. And so the refractive index only slightly differs for different wavelengths of visible light. That makes sense to all of you? So it's slightly different for blue light. For a given medium, it's slightly different for blue light than what it is for red light. All right, so the refractive index depends on the material, and it also depends on the wavelength of light that's propagating through the material, right? All right, and a convention is that sometimes when you have a larger n, so one medium has a larger value of n than the other medium, you sometimes just call it optically denser. So that's just a convention. So that's easier than saying larger value of n. So for example, water is optically denser than air because water has a n of 1.33 and air has a n which is very close to 1. So we would say water is optically denser than air. That clear to all of you? So the index of refraction for a certain medium is the speed of light divided by vacuum divided by the speed of light in vacuum divided by the speed of light in the medium. That's the definition of n, and it depends on the medium. It also depends on the frequency of light or wavelength of light. That clear to all of you? Okay, so it's more convenient to express Snell's law in terms of n. So we've just seen that V is equal to C divided by n, right? So if this medium has n of n1 and this has n of n2, right? N value of N2, then you can see that V1 divided by V2 is equal to, I'll just write it over here, V1 divided by V2 will be N2 divided by N1, because V and N are inversely proportional to each other, right? So instead of using V's, it's conventionally, Snell's law is expressed in terms of N's. And so Snell's law is written as N1 sine theta 1 is equal to N2 sine theta 2. So this is the way Snell's law is usually written, right? But this is also Snell's law. So they are both Snell's law. Is that clear to all of you? All right. So Snell's law is the law of refraction. Okay, so we just talked about this. All right. I'll let you do this plug and chug problem yourself. It's also worked out on the slide. All right, let's try this question. The question is asking whether it's bending away from the normal or towards the normal. All that means is the angle theta 2 greater than the original angle of 30 degrees? Or is it less than the original angle of 30 degrees? Because if it's greater, then it's going to bend away from the normal. And if it's less, then it's going to bend towards the normal. So we just need to figure out what is the relationship between theta 1 and theta 2, right? Is theta 2 greater than theta 1, or is it less than theta 1, right? Greater than theta 1 would mean away from the normal. Less than theta 1 would mean towards the normal. So to answer that, we just apply Snell's law. So N water sine theta 1 is equal to N air sine theta 2. And so you can see that sine theta 2 is equal to N water divided by N air sine theta 1. And you know that N water is larger than N air, right? And so N water over N air will be greater than 1. And so you can see that sine theta 2 will be greater than sine theta 1. That makes sense? And so if sine theta 2 is greater than sine theta 1, you know right away that theta 2 is greater than theta 1, because you know that in the first quadrant, sine theta and theta behave more or less the same way. If theta goes up, sine theta goes up. So if sine theta 2 is greater than sine theta 1, then theta 2 is greater than theta 1. All right. You can see it without even writing this down. You can see that this relationship sine theta 1, N1 sine theta 1 equals N2 sine theta 2 can be written like this. Sine theta 1 divided by sine theta 2 is equal to N2 divided by N1. In other words, sine theta is inversely proportional to N, right? And since theta and sine theta behave in more or less the same way, you can loosely say that theta is inversely proportional to N. So when N goes up, theta will go down. And if N goes down, theta will go up. So that's another way of seeing the same thing. That makes sense? All right. So a ray will bend towards the normal if the second medium has a larger index of refraction. So if it's going from an optically rarer to an optically denser medium, then it's going to bend towards the normal, like what's happening over here when it's going from air to water. Now you can see that theta 2 is less than theta 1 because N2 is greater than N1. And so the ray is bending towards the normal over here. And in this case, when it's going from a optically denser medium to an optically rarer medium, the N is decreasing. So the theta, the angle of refraction is increasing. That makes sense? So in this case, it's bending away from the normal. So there are many consequences of refraction all around us. Plenty of examples. One example is consider this fish in the aquarium, right? In this little aquarium. So a ray of light from the fish goes like this. Then it hits the air-water interface, and as a result of refraction, it bends away from the normal and goes to the person's eye. Now, we'll see in the next chapter that our eyes are not very good at following bent paths of rays. So what our eye does is that it can't deal with the fact that the ray has changed direction. So our eye and our brains basically just produce this ray backwards and imagine that it started from over here, whereas it actually did start from over here, right? So we will see the tail of the fish from which that ray started at that elevated position. That makes sense? And that applies to every point on the fish. So we will see the fish over here rather than over here where it actually is. That makes sense? And so if you try to catch the fish, then you will miss because the fish is not actually over there. So you have to put your hand a little bit lower in order to catch the fish. People who do spear fishing have to deal with this all the time. So they know that the fish or whatever they're trying to hunt is not exactly where it seems to be. And from practice, they know exactly where to aim the spear. Uh, that clear to all of you? Another thing that you might have noticed many times is that if you have an object that's in a cup of water, like the straw, it appears to be bent. You can clearly see how the straw appears to be bent. The reason why the straw appears to be bent is exactly the same. So here is the cup of water, and here is the straw. A ray of light from the straw will follow a path like this, and it'll get refracted and go like this, and then it'll be picked up by the eye of the observer. Now, the eye of the observer is not very good at following bent paths of rays, and so that's just how our brains are wired. So the eye will just produce this ray backwards and conclude that it started from somewhere over here. So the bottom of the straw will appear to be at an elevated position, and that applies to every point of the straw underwater. So the entire submerged part of the straw will look like this. That clear to all of you? That is why the straw appears to be bent. Is that clear? That makes sense? All right, so for a similar reason, the apparent depth of something is different from the actual depth. It's exactly the same reason. The refraction of rays, a refraction of light causes the rays to change direction, and our eyes are not able to follow the bent paths of the rays. And so we think that the bottom of this glass is over here, whereas actually it's over here. All right. So there are many other, here's another application of consequence of refraction. So this is a standard beer mug, and you can see that it seems to be filled with root beer, right? However, if you immerse this beer mug underwater, right, you can see that a lot of it is actually glass. So the fact that it's completely filled with beverage from here to here is an optical illusion. Glass is quite thick, and so the beverage only goes from here to here. That makes sense? Which is very great for a person selling this beer, because their customers will think that they're getting a lot of beer, but actually what they're getting is much less than it appears. So what happens is the rays of light are actually starting from over here and over here, but as a result of refraction in the glass, they change direction and they appear to start from over here because the glass makes them change direction, and our brains are not very good at following curved paths of rays, and so our brains assume that the rays are actually starting from over here. That is why we see the glass. It appears to us that the glass is completely filled with beverage. If you submerge the glass in water, then water reverses that effect. And so as a result of that, or it cancels out that effect of refraction. And as a result of that, we can see exactly where the rays are starting from. Another application of refraction is the following. Here is the Earth, and here is the atmosphere of the Earth. Okay, this diagram is not to scale at all because the radius of the Earth is 6,400 kilometers, and the thickness of the atmosphere is at most 100 kilometers. After that, it's really thin. So this is so the atmosphere is a very thin skin over the Earth, extremely thin skin over the Earth. All right, right. So suppose you are over here, you're standing over here, and it's sunset. So that means the sun is about to sink below the horizon. Now, if the sun, this is the sun, and it's about to sink below the horizon for you, the Earth is rotating this way. So you're watching sunset, right? Now, as a result of refraction in the Earth's atmosphere, the rays of light will bend as they pass through the atmosphere. They will change direction a little bit. So they were going this way, but after refraction through the atmosphere, they will go this way. So they change direction a little bit. And as a result of that, you will see the sun even though it has sunk below the horizon for you. So our eyes will follow the bent path of the rays and conclude that the sun is a little bit higher than it actually is. And so you will continue to see the sun even though it has actually sunk below the horizon. So keep that in mind the next time you watch a sunset. Remember that you are seeing the sun as a result of refraction through the atmosphere. The sun is actually not visible anymore. If you didn't have an atmosphere, you wouldn't be able to see, you would see the sun is completely set. That makes sense to all of you? Um, and does anybody know why sunsets are red? Like, why does the horizon look red at the time of sunset? Or why does the sun appear to be orange or red at the time of sunset? Does anyone know that? Nobody knows that? So I just want to confirm that nobody knows that. All right, okay. So I'm happy because then I get to teach you something new. The reason that the sunset appears red is the following. The rays of light from the sun have um, have a lot of visible light, all right? What we call visible light, which is light with wavelengths between 400 to 750 nanometers. 400 is blue, and or indigo, and 750 nanometers is, and closer to 750 nanometers is red. The sun also gives off other wavelengths as well, but it mostly gives off the visible part of the spectrum. That's the type of radiation that it gives off most of all. So our eyes can only respond to this part of the spectrum, right? Anyway, so all of these wavelengths come out from the sun, but as it turns out, when they pass through the atmosphere, um, they interact with the molecules of the atmosphere, right? And what the molecules of the atmosphere do is that they scatter these rays. So scattering means that the rays just essentially bounce from one molecule to another. Now, if the wavelength is small, like in the case of blue, then the scattering effect is more pronounced. So the blue light, so if these are molecules of air, blue light is going to, the shorter wavelength light is just going to bounce like crazy between molecules. It'll just keep on bouncing and bouncing between molecules. And so it will not be able to travel very far, right? Because it's just too busy bouncing around from molecule to molecule. If the wavelength is long, like red, it doesn't scatter that much. So the red light will scatter a little bit, but not as much as the blue light. So it's easier for the red light to cover more distance than it is for the blue light, right? And so when the sun is setting, the amount of atmosphere that the rays have to cross, the light has to cross, is clearly much longer than if the sun were directly overhead, right? And so all the other colors of light get scattered away, and it's only the longest wavelengths that are able to make it through. And that is why this horizon appears to be red. That makes sense to all of you? That also explains why the sky is blue. So if this is the Earth and this is the atmosphere, when the sun is directly overhead, the rays of light from the sun have to cut through only a small swath of atmosphere, only this much atmosphere, right? And as a result of that, the blue light, which is scattered all over, still gets to you, because it's not too wide of an atmosphere that it has to cross, only about 100 kilometers of atmosphere. Whereas in this case, it might have to cross several hundred kilometers of atmosphere in order to get to your eye. So over here, So that is why when you look at the sky, you see blue light coming from all directions, because the blue light is scattered like crazy. It's all over and it's coming at you from all directions, and that is why the sky appears to be blue. That makes sense to all of you? And the red light, which gets to you directly, is easily overwhelmed by the blue light that's coming from all directions. So your eye completely ignores the red light that's coming towards it, and it just sees the sky as blue. That makes sense to all of you? All right. Now, the shortest wavelength of light is not actually blue. 400 nanometers is actually indigo, which is a deeper blue, I think. So, but the reason that we see the sky as blue has to do with the way our eyes work. So our eyes are not very good at perceiving indigo, but they're much better at perceiving blue. So we just think that the sky is blue. That makes sense. Whereas the actual color is not really blue.